Hello everyone, my name is Elisa Baum. I'm Percona's Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct a bit of housekeeping. Could you please use the hand icon located in the GoToWebinar control panel to let me know if you can hear me? And let me take a look. Do I see any hands? Oh, I see a couple hands. That's perfect. Thank you very much. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. If your question is related to material on a specific slide, please make sure to indicate which slide you're talking about, just to make it easier for Bill to answer questions. At the end of the webinar, we will take time to answer as many questions as possible. Questions that are most relevant to the topic we're discussing today will be answered first. Those that aren't addressed will be answered in a follow-up blog entry on Percona's MySQL performance blog. In addition, I will make sure that each and every one of you gets a recording of this webinar within 48 hours. With that said, I'd like to thank you for attending today's webinar, How to Avoid Even More of the Common but Deadly MySQL Development Mistakes, presented by Percona Senior Knowledge Manager, Bill Carwin. Bill, you have the floor.
Thank you, Elisa. Thank you, everyone, for joining me. This is Avoiding Even More Common but Deadly MySQL Development Mistakes. We've been doing a series of webinars, and they've proved to be pretty popular, so there's plenty to say in this topic area. So this will be a roundup of some more of the real deadly mistakes. What do I mean by this? Is the common but deadly mistakes are the frequent mistakes that we see over and over again in our experience doing support and consulting for MySQL sites and users. And these are committed by either inexperienced developers who don't know MySQL deeply, and they make mistakes not knowing that it's going to have a high cost, or folks who are cutting corners. They're trying to get their work done more quickly and maybe not following best practices. Or they are experienced with MySQL and they're trying to do a good job, but there are some internal behaviors that MySQL has that are not widely known, and they can kind of trip you up. And this just comes with experience or by contacting some experts like those at Percona. The first topic that I want to cover today, I call it Select Wildcards. This is probably pretty familiar to you. Let's start out with the simple ones today. When you use a select query in SQL, it's a very common pattern to just query for all columns. It's quick and easy. You don't have to do a lot of typing, and it gets all of the data, in fact a superset of the data that you would need for a given task in your application. So what's wrong with this? Well, does your application really need all of those columns? It's typical in an application that you may only need a couple of columns from a given table in order to solve a particular task. And this comes up especially if you've got bulky data that is less commonly needed for any typical query. You might even have maybe an image in your table that is very bulky, many kilobytes for a blob, for example. Do you need to download that from the database server to the application server every time you touch that table? Probably not. It could also be a problem if the column names or positions change in your table design. And if you just did select star, you'd get all of them, but they'd be ordered in different ways in your result set. And if your code is expecting them to be ordered by a particular name or in a particular position in the result set as it fetches it, it could confuse your application in hard to debug ways. The issue about downloading all this information is important because while we are accustomed to network bandwidth being large, especially if we're upgrading to gigabit networks or even 10 gigabit networks, it's still finite. There's still a limit on how much your application can fetch from the database in a given second or millisecond. And if you've got many different sessions going on concurrently, that just multiplies. We have pretty commonly seen cases where folks are fetching too much from the database, either too many columns or too many rows, and they exhaust the network bandwidth, and then it slows down their application. If you treat the network as a finite resource and try to be frugal about that, it can be better for your performance of your application. So I show wildcards in my example queries when I'm doing presentations or demonstrations, but that's just for testing or for brevity. If I am writing production code, I never use wildcards. I name the columns explicitly. So here's an example where I show select username, comma password hash from users. Those are the only two columns that I need for this particular query, and I omit the rest. You can also use wildcards on a per table basis, which people often overlook. Maybe you only need one column from the users table, but you need all the columns from the privileges table, and it can be a useful shorthand to specify the wildcard for just the privileges table. There's an example here on the slide. Here's another one that I see come up frequently, ambiguous groups. In a query such as this one, where let's see, I'm looking for my forum posts and I want to get the forum ID, the user ID, and the max date posted. So maybe this is querying for the most recent post in a given forum and the user who posted it. Problem with this is that it doesn't actually return the user who posted the most recent forum post. It'll return one of the user IDs who posted to that forum, and it'll return the date of the greatest forum post. But the user isn't the one who posted that one with the greatest date. Very confusing. It should infer what I mean from this. It doesn't do that. So let me show you a different example that may illustrate the reason here. If I'm doing a query similar to the one on the previous slide, and I'm looking for the maximum of the posted date and the minimum of the posted date, two aggregate functions in the same query, and then the user ID. So should this return the user ID who posted the most recent or the earliest post from that forum? In fact, it does neither. It returns the user ID who was one of the users, but it is chosen arbitrarily, probably in just storage order from that table. To try to solve this, if you're doing a query with group by, follow what's called the single value rule. And that is, if you have a column that's in your select list for a group by query, it has to solve one of three rules. Either be in the group by clause, and here's an example where the column forum ID is the same column that's in my group by clause. So naturally there would be one row returned from the group by for each distinct value of forum ID. Or a column must be inside of a grouping function, like max or count or sum or average. That's okay because it'll be a group-wise calculation based on the range of values found in each group. Or if you can guarantee that there's only a single value in that column, you can return that as well. And here's an example. I'm doing a join here. Forum posts join to forums, so that the canonical list of different forums, and then if there's a forum ID and a forum name. If I'm grouping by the forum ID, then forum name is functionally dependent on the forum ID being the primary key of that forums table. And therefore, there can be only one value for a given forum ID. It will only give one name for each forum ID, and therefore it's unambiguous, and we can be assured that it will return the correct one. That doesn't show us the user ID who posted that max value. That's a different problem. But this is just demonstrating the way to get around the ambiguous results from group by. Another mistake, micromanaging queries. This is one that I see pretty frequently, and it came up when I was reading a blog by a user who said they were a group of developers who had just finished launching their startup company, and they posted a blog saying lessons learned about managing and developing with MySQL. And one of the statements that caught my eye that they said was they claimed always use force index. And this is a thing that led them to be able to use the indexes more effectively, they thought. So what is that force index all about? It's called an optimizer hint. The MySQL query optimizer is meant to do an automatic discovery of which index is going to be the most effective to use for any given query. And it does this analysis on every time you execute a query. It's supposed to be automatic, but occasionally the optimizer makes a wrong decision. And there can be some corner cases where we need to give it a little bit of a nudge. There's syntax, force index, use index, ignore index, and also one called straight join, which allows us to override the optimizer's choice for the order in which it accesses tables. So the straight join means don't reorder the tables, read the tables in the order that I specify them in my query. So these are optional keywords that you can use for queries and override the optimizer's automatic behavior in cases where it doesn't do the right thing. But the blog that I read who said always use these index hints was exercising too much of a good thing. They can be useful in the right circumstances, but they should really be considered the exception rather than the rule. The disadvantages of using index hints are that you end up hard-coding your index names. You say use index or force index, and then you name the index name that you want the query to use. But this means that now your application code where your queries are written contain hard-coded index references. And if you ever change the indexes, rename them, drop them, add new ones that should be considered, now you have an additional chore of going and finding all the places in your application code where you had mentioned that index name and changing that code. So it complicates your development process. And this presentation was about developer mistakes particularly. It also ignores the fact that the same query may use different indexes naturally in different situations based on the conditions that you use for searching. The specific values that you're searching for may appropriately use an index or not use an index, and the optimizer is designed to try to figure that out on a case-by-case basis. By specifying the index in a hard-coded way, you remove the optimizer's opportunity to do that. There are also cases where an index that you name in your query is not the best index for a given query anyway. Here's an example. I'm doing select from forum posts. I'm specifying an index hint saying use index post, but my condition is on user ID. If I'm searching on user ID but telling the optimizer don't consider any other index other than the one on the posts column, then it can't consider what would probably be the better index if there is one on the user ID column. And this can actually be harmful to your performance in a great deal. If you tell it only consider the index on post, it can't use the index on post because that's not the search criteria that you have, then it has to resort to a table scan. And that's very expensive. There are also some queries where it doesn't matter how much you urge the query to use a particular index, it's still a query that has to scan the whole table anyway. So here's an example, select count from forum posts. And I really try, I can even say force index to be even more vehement or forceful, and still it will do a table scan because that's what it needs to do for that query. So using the index hints doesn't truly force it to use an index in cases where the index is not useful for that particular query. Be conservative with optimizer hints. Don't overuse them. Treat them as an exception rather than the rule. It's better to do some query analysis and choose the right indexes to let the optimizer make an intelligent choice. Reducing the hard-coded naming of indexes in your queries means your application is more abstract and easier to maintain. You don't have to change the code every time you add an index or drop an index. And also, keep in mind that every release of MySQL, every major version, 5.5 to 5.6, 5.6 to 5.7, and so on, the developers have improved the optimizer to make it smarter and use indexes better in the right situations. So if you do use index hints, it would be worthwhile if you're preparing to upgrade to a new major version of MySQL, prepare a test environment with your application code, take out all the index hints, and see if the new version of MySQL makes smarter decisions in the cases that you did have to override with index hints. Here's the next mistake. Self-documenting schema. We don't need to write documentation because the code is self-documenting. Is it really? Naming columns and tables is really difficult. It's one of the biggest problems in computer science. You know, remember the old saying, what are the two problems in the unsolved problems in computer science? Cache invalidation and naming things. So names are difficult to come up with a good way to make it clear to everybody. Everybody has a different interpretation. Here's an example where we have columns name. Well, who does that name? In this table, does it name the person who created the account? Does it name the account itself? Does it name something else entirely? Status. What are the set of valid values that status can take on? Entity num. Wow, that's really generic. I don't have any idea what you mean by an entity or a num in that context. I can guess, but maybe I'm not right. And order. Is order referred to sort order, or does it refer to like an e-commerce order, like an entry in your shopping cart? It's really not clear from just these. One of the features that people seldom use in MySQL is to actually put comments into the metadata for tables, columns, indexes, and partitions. One of the reasons that this has not been more popular in the past is that the length limitation on comments was pretty short. But in 5.5, they increased that a great deal. So now you can write about 1 kilobyte, 1,024 characters in those comments, and that makes them more useful. Yeah, you could actually describe the proper usage of the tables and columns that way. The syntax is part of the create table syntax, so you can specify the comments there. You can also alter a table and add or change a comment after creation time. And I tested to make sure that changing the comment does not trigger a table restructure. So it's a very quick online operation. It doesn't have to rebuild the table to change a comment. And so you could put a comment on every column if you wanted to, and be very clear about how it's used, maybe references to other parts of the database. Here's the order column. Now we understand. It's a reference to the orders table. It's actually a foreign key. Documenting the schema in this way, either in comments or in a conventional way as a document that's kept offline, tracked by the project, you can describe the proper usage and intended rules for the tables and columns in your database, and this can greatly reduce the time that it takes to educate a new developer on your team. Otherwise, they would have to be asking questions individually and bugging other people to come up to speed. Also, encouraging documentation may, as a side effect, encourage proper use of naming conventions. If you've got naming conventions for your tables and columns, it makes it more likely that people will follow them if they also have to think about people reading documentation about the tables and column names. And finally, by reviewing the documentation, it may make it more easier to periodically identify obsolete columns and obsolete tables that should actually rightly be removed from the database. If the comment or the documentation for your metadata describes a process that your application no longer does, then somebody says, oh, well, this data is totally obsolete now. Here's a database design mistake that we see pretty frequently. I call it de facto queue. Using the RDBMS as a queue. Let me describe what I mean by that. There's a common pattern that if you have rows of data that need to be processed, you can insert them into a table that serves as a queue, so that you just add new rows to the tail of a table, and some other process is periodically going and picking the first few rows off the head of the table. Here's an example where we do a select from the queue table where state equals unfinished and pick the first one. and then do a for update to force it to be locked. Therefore, my session is going to get exclusive access to that particular row. And then we do some work on our application, and then finally set that row into a state of finished. And we may have even multiple sessions doing this kind of processing in concert, as long as they're all picking off unlocked rows and with a state of unfinished, then they can continue working. And then periodically, you may even prune the table by removing all the finished rows. Very common type of pattern for using databases. However, what I found is another alternate, excuse me, let me describe this alternative method. If you don't want to rely on the for update to lock things, you can set a in progress state for a given row in there, and therefore nobody else should be able to pick that off with their select statement. They won't match their query for unfinished items. And then your session would work on this particular row that you have marked in progress, and when you're done, you can then change it to finished. As you insert more rows to the table and delete rows off the end, the pattern for the internal B-tree index is that you're continually advancing the ID and removing those on the other side of the B-tree index. And this can actually, over time, cause an imbalance in the B-tree. The B-trees are designed to try to stay in balance roughly, but it's still a bit less efficient to be continually growing and pruning that B-tree. It tends to get lopsided. I also found that trying to use a select for update with a limit clause, you would think that it would lock only the row that is returned by the limit, but in fact it locks all the qualifying rows, even those beyond the limit, and it keeps them locked for the whole duration of your query. So you might as well be doing a table lock pretty much. The alternative method, where you set a in progress flag until you're finished with the row, this has a risk that if the session that performs that marks it as in progress, but then crashes or exits abnormally, that row does not revert back to an unfinished entry in the queue. It sort of goes into a limbo state where nobody's working on it, but it's still marked in progress. And then you would have to have some task to clean those up and mark them as unfinished if they are detected as being idle. What's the solution to all this? An RDBMS primarily isn't the right technology for doing a queue-type work pattern. There are other specialized storage engines that are called message queues, and they are better suited to this pattern. They know how to do a publish and subscribe. They know how to store progressive data without getting an imbalanced index. They can assign responsibility to a worker to continue to have exclusive access to a given job entry. And they're even distributed message queues so that you can have greater concurrency. You don't have to do locking of the entire queue, etc. So those are specialized tools for that particular purpose. They're not capable of doing the type of structured data representation that a relational database can, but it's very good for this type of first in, first out kind of workload. There are a bunch of options now on the open source market. We tend to recommend open source tools, and here's a whole bunch of links for you if you want to try to read up about some of those. Some are better suited for certain types of projects than others. Some are written in PHP or in Java. So choose the one that matches the technology stack that you have for your project better. One of my colleagues in Percona Consulting wrote a recent blog article exploring message brokers, where he evaluated a few of those and how they're used with MySQL workloads. So I encourage you, if you're interested in this topic, to go start with his blog that I linked to here and read more about it. Premature sharding. One of the frequent questions we get is how do we decide when to do partitioning and sharding of a table? And I'll try within a few minutes to give you an introduction to that here. We all have heard this saying, premature optimization is the root of all evil. which is to say trying to solve a performance bottleneck before you can actually prove that it is a bottleneck is probably wasted effort, because you may never experience that as a bottleneck. Your time is better spent focusing on the actual problems rather than trying to prepare for one which will never occur. That said, it applies to optimizations in a big way. So keep this saying in mind for the next few minutes. What do I mean by optimization of database structure? All the techniques that we have for database optimization these are good examples of them, and they are all designed to try to solve the performance or scalability for specific queries. That is, all of these techniques kind of depart from having a logical design for your database with rules of normalization applied to design the tables. These are all exception cases. Designing indexes is actually a form of storing data redundantly. We just have the convenience that it stays updated when we make changes to the base table. Denormalization is also storing data redundantly to avoid expensive joins or functions or group bys. And then partitioning and sharding are ways of splitting up data so that we can access a smaller subset of it instead of having to access a very large table to search for what we're looking for. Why don't we just optimize for everything? Why do we fail to optimize? The reason for that is that any case of optimizing for one specific query type comes at the expense of other queries. That is, I can say I need to be able to search for the users who posted to my forum, but I don't necessarily need to always query for which forums did that particular user post to. Those are two different ways of querying the same data. One is, given a forum, give me the list of all users who posted to it. The other one is, given a user, give me the list of all forums that they posted to. So same root data, same base data, but two different ways of looking at it. I could optimize for one of those, but and probably achieve that using an index or a denormalization or one of the other techniques. But the flip side, trying to do the other type of query against the same data, may actually be degraded by my optimization. A good example of that is denormalization. So you need to know the queries in your application. You don't necessarily have cases of all those different ways of querying the same data. You may have some that are more frequent or more important to be optimal. And therefore, it's justified to try to optimize for those, even if it degrades the others, because they are either less frequent or not present in your application at all. It's not important if you degrade those other queries, because they are simply never run. So when do we do partitioning? Mostly this benefits read queries. The partitioning is making a logical table into separate physical subsets of the table, so that when we do a search based on the criteria that is the way that we partition the table by, then it can narrow down the search very quickly by only considering the partitions that contain that. For example, if you partition a table by date, and then you could do a query by date, say only consider the partitions that are in the last week, and that would be a very common type of way to do partitioning. It can therefore exclude all of the historical data that is earlier than 1 week ago. And this can actually cut down on the overall performance or cost of the query even more effectively than indexing. There's a great presentation by Giuseppe Maggia where he shows some examples of that when the partitioning feature was being introduced to MySQL. And he did a presentation. You can still find it on SlideShare, where he did some benchmarks and found that he could improve things with indexing by an order of magnitude, but with partitioning, it would be maybe 2 orders of magnitude of improving the performance. And of course, you could have both. You could have indexing in addition to partitioning and get both benefits. Why wouldn't you partition? Well, like I said, you could have different queries on the same data. And you might have a mix of queries that are going to be accessing the data in different ways. But you can only partition a given table in one way at a time. You could partition it by date, for example, and therefore if you search the forum posts for a specific user, it would have to search every single partition because it doesn't necessarily know that the user, his posts only fall into one particular partition. So that's what I mean by when I say the search criteria, the conditions in your where clause have to cooperate or be matching with the way that you partitioned the table. Otherwise, there's no benefit to the partitioning. You can still do those queries. That's one of the nice things about partitioning. It will actually automatically search all the partitions if it needs to, but just don't expect it to be improved in performance if it has to go to that extent. It only improves in performance if it's able to accomplish partition pruning by narrowing down which partition your data is living in. What about sharding? Sharding is kind of, in a way, it's similar to partitioning in that it splits up a table or splits up a collection of data that's similar. But in sharding, we typically put the subsets of that not as transparent, physical, separate partitions in the same table, but we actually put them on different MySQL instances, probably on different servers. The reason to do sharding is often for write queries. This is where sharding really is appropriate and gets its best benefit. If you have such a high rate of write traffic to your table that you simply can't go any further because the physical limitations of the server can't handle it. It can't do that many queries per second. The disks can't do that many I/O operations per second. You've hit a wall. Well, the way to scale out there, you could either invest into very, very expensive hardware and try to scale up, but you could also split up the data so that only a certain percentage of it is being written to on any given MySQL instance. So it's a way to distribute write queries and increase your capacity that way. Why wouldn't you do this? Well, again, like the partitioning, you might have a mix of queries that naturally span many shards, so that if you're updating a set of rows, or if you're selecting to read a set of rows, it may actually have to visit multiple instances of MySQL to get the full result set either written to or read from. Sharding makes a situation where it's much more efficient if you're doing individual row updates or reads. Once you start doing range queries like between or greater than, it will have to start touching probably all of your shards, and therefore the cost is actually pretty high. We've done some benchmarks that show that the more shards you have, the worse it gets, not even linearly, but as a exponential or geometric progression. So be very careful that you have an application that's designed to primarily do row-by-row operations. Each given query may update or read an individual row, therefore the choosing which shard that data lives on is a quick operation, and you can prune out all the other shards for that particular query. Also, a reason not to shard is that at least to date, there have been very few solutions that provide a transparent mapping between data operations and which shard the affected data lives on. So you end up having to write a lot of custom code in your application and decide on how you want to split up the data and how to find it on any given query. It makes a lot more coding work for you as a developer. That's starting to change now that there are a few tools out there to solve that problem in a more automatic way. One of the solutions that's coming from the MySQL company is called MySQL Fabric, and that's still in its early development stages, but it's worthwhile downloading that early access release and testing it out and exploring that. Again, like any sharding architecture, it doesn't really work very well if you do range queries. So it's best if you're doing one row at a time. Another solution is shard query. which is a solution developed by a Percona consultant, Justin Swanhart. And he has developed, he's actually got about 3 years of advanced work over MySQL Fabric. So he's developed a very sophisticated query proxy that can map your query transparently into finding the data on the respective shard. And that's also worth checking out, Shard Query. You can find some mentions of Shard Query in our MySQL performance blog and also Shard Query website. One thing to keep in mind that sharding also introduces as cost is that operational cost is increased. It's more expensive and more difficult to manage multiple database servers than just a single server. And this is where the Donald Knuth quote comes in. Don't try to go directly to a sharded architecture if you haven't made use of a single instance architecture to its best advantage. We've seen many cases where people don't tune their MySQL instance very well, or they don't analyze their queries for optimization very well, so they're actually using the MySQL instance very inefficiently, and they could go a lot further, probably years of growth in their project without having to adopt a sharded architecture. Not everybody is Facebook. We've written about these sort of principles in the past. There's a couple of blog posts from the Percona managed MySQL performance blog. Keep it simple, kiss, 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 and why you don't want to shard. And those are a couple of good blogs with food for thought about whether you should adopt sharding as an architecture or not. Let's keep going. Security holes is the next topic. When thinking about security for our databases, we often focus primarily on data access. We want to have policies about strong passwords or maybe password recycling. We are very focused on access privileges with the grant and revoke statement, and users being granted the minimal privileges to access the data they need, but not the data that they shouldn't have. We think about encryption for the connections using SSL or VPNs, or we want to have encrypted data storage or an encrypted file system, and that's all possible too. And then finally, firewalls to disable access from anybody but the authorized applications. So it's all focused on data access. Where's the weak point in this type of architecture? Something you may not have considered, that the database isn't the only place that sensitive data may reside. Also have to have your security plan include anywhere else that the data could end up. And here's some examples. Backups. Do you store the backups in a secure way? Could somebody get access to those? I've seen sites that have very strict security, but then when they have media where they've stored a backup on DVD-ROM or on tape or on another storage mechanism, and that becomes an obsolete storage, they just throw it in the trash. So somebody who wants to steal your data, they may get some data that's a few weeks out of date, but they can actually literally go through your trash and find the recycled media that you stored old backups on, and that can be dangerous. Logs. Query logs, error logs, anything that has data that's generated by your application may have samples or individual entries of sensitive data. How many people have gone through the query log and seen a whole list of insert statements or update statements that were responsible for creating values in the database and may have sensitive information like plain text passwords, or that's another insecure practice, is storing passwords in plain text, or could store other sensitive data like credit card numbers or important information like that. If you have compliance requirements to make sure that nobody gets access to the database, you also have to think about other places where those values could appear. Reports. We are advocates at Percona of using query analysis and doing reporting based on the logs, but the reports often actually contain sample queries as well, and those could be queries that contain sensitive information. And finally, if you use a copy of your database in a staging environment or test or development, it's very common to take a copy or maybe an old backup so you can have a quantity of data to test with. That could also have sensitive data. So build that into your security policy. And account for the whole life cycle of your data. Ask questions in your security policy, like how do you store backups and archives and logs? How do you dispose of those when you do that? Who has access to all those copies or even logs or reports? Before you share any data, do you have any tools that you can scrub or obscure the sensitive data? Maybe it's just as like if you wanted to copy the database to a test environment, you would then null out any of the columns that have sensitive data, like credit card numbers. Or if you do need to do testing, do you have some tools that can generate artificial data that's not taken from production data? It just simulates it, but it's all random values. Synthetic data, I call it. The point is, if you have a security policy, you need to be comprehensive and take into account all places that the data can migrate to, and you need to follow it. You need to not only write it down, but then you need to adhere to it and do that consistently. Security is only as strong as its weakest link. Next topic, trivial testing. We frequently see people do testing in a development cycle by inserting just a few rows with dummy values that aren't very representative of their production traffic. Here's an example where somebody just created two rows of data into a table, and it really only relates to a single forum ID in their forum posts and just two different users, and then artificially short content, where the text for this forum posts table may allow for a long content, but these only have a couple of words. And then say, okay, that's enough. Let's begin testing the application. So this has, it's very easy to set up. It's tempting to do this, but it has some costs to it. For example, the optimizer for queries may give atypical estimates if you have too few rows to test with. It may decide, oh, well, this table only has 2 rows. I'm just going to do a table scan because it's going to be, all the rows are on a single page anyway, so there's no need to use an index. Whereas if you had a realistic quantity of data, it would actually be forced to do something more efficient, like use indexes. Also, selectivity is important to the optimizer. If it can tell that you're querying for a given forum ID, and that's accounts for 100% of the rows in the table, then it may decide not to use an index to search for that forum ID. If, in fact, the selectivity, it has a breakpoint close to 18 to 20%. If it decides that you're searching for a value which occurs on more than 20% of the rows in the table, it will just decide to use a table scan and skip the index because it's more costly to use the index as a separate lookup than it is to simply read the table from one end to the other. 20% seems a little low for that reason, but it ends up being not a bad estimate. So the point is to, when you're doing testing and development, have a significant amount of data in your tables before you rely on the results of testing for performance and query optimization. I like to say, rule of thumb, 5 to 10,000 rows of data is more than adequate to trigger that. Maybe even fewer in some cases, but you want to have a pretty good quantity to demonstrate that. And also have a distribution of different values in that table. Don't have everything be forum ID 1. Have something that's going to be similar to what your production site is going to store. A couple of different tricks to do this. What if we could take a sample of our production data? Maybe the full production data would be most representative, but it's too large to copy to every development environment. One trick I've used is using MySQL dump with a option --where, and then you can apply an expression to the search criteria for each table. And here I used random number times 100 is less than 2. Therefore, this will be a true where predicate on 2% of the rows that it finds in each table, a random 2% sampling of each table. Therefore, I can make a copy that's only 2% as large as my production site. That can be good for a single table, but the risk is if you have related tables, then it's very unlikely, this random sampling, that it will actually select for rows that actually match up to one another in the relationships. So that's not a perfect solution. I have not found a tool that can take this sort of random sampling but also preserve relationships between related rows across multiple tables. That would be an interesting tool, but I haven't come across one that does that automatically. You can may have to do that as a homebrew project to roll your own. Also, same issues with privacy and security that we talked about earlier apply. If you're taking data from your production data, you have to be sure to scrub it or take some steps to make sure that it doesn't include sensitive or private data. Another option is to use synthetic data generators. One nice one that I've come across, it's open source and free. It's called DataBean Generator, and it's an application that you can feed rules for the patterns of data that you want to generate and then populate your database with that. So explore that if you want to find a nice open source tool for generating random simulated data. Another naive testing is testing with not only dummy data, but dummy load. That is, in development and testing, it may be tempting to just do unit testing or functional tests to see if your application queries work correctly. But some problems appear only when you're running many threads concurrently, and that happens when the threads are in contention with one another. For example, doing table locks against that are causing each other to serialize. Or resource use by one thread is insignificant, but multiply that by 1,000 threads and it can cause significant load. So this is the difference between functional testing and load testing. You need to do both types of testing to really have a great deal of confidence in the code. There are a number of different load testing tools you could run in a staging environment or a test environment to try to either simulate or replay a log of requests and then replay them in parallel to simulate load. You can do this, there are tools to do this at the web request level that can drive a application simulating a browser hitting a web page multiple times. And here are a couple of options that I've used, JMeter and Siege. I've also done some homebrew tools like that. Or you could actually do it bypassing the application layer and going directly to the database level. If you've got a log of all the queries that were collected during traffic when you had the general query log or slow query log enabled, or the binary log, you could replay those against instance and even do it in a multi-threaded fashion. And we used to have a tool, part of the Percona toolkit called PT Log Player, but that's being phased out in favor of a much more robust and featureful tool called Percona Playback. You can go and take a look at those and experiment with those. And finally, if you have very special needs for simulating load, you may have to roll your own within your own project. That is, create your own automation scripts to drive your application. And it may partially use some of these other tools like Percona Playback or JMeter, but it may also have other logic that you need to implement that's more specific to your site. Not only performance, but also resource use is good to measure during these load tests, and queries per second to see if not only the time it takes, but also the throughput, which is a slightly different way of measuring the overall performance of the site or the scalability. And then graph those figures against how much load you're simulating with these playback tools. This can be a good way to try to see if you have a scalability wall. That is, you can keep on increasing throughput up to a certain point, and then the resources top out and you can't go any higher. It'd be good to know what point that is so that you can on a day-to-day operations basis, see if you're close to hitting that wall. Another good strategy or best practice is in your load testing, try to go much higher than your anticipated production load. Therefore, you know that you have a system that can handle unforeseen spikes in traffic or just natural month-over-month growth in the traffic. Most sites have an increase in the amount of data and the amount of traffic that they're going on if they're successful. And you want to be able to say, we have the capacity to handle growth for the next 12 months or even 3 months would be something that you'd like to be able to say. Another good best practice is if you've got failover procedures, if you've got high availability requirements and you need to be able to test failing over to a new server, make sure that your procedures can happen when your load testing tools are running, because it's more likely for failover to be required at a time when load is high. That's often when something goes awry and you need to fail over. And finally, the last topic I'm going to cover today, I call this modeling the universe. And this was inspired by a quote that I read from Carl Sagan. If you wish to make an apple pie from scratch, you must first invent the universe. It's my best Carl Sagan impersonation. What do I mean by this? Well, let me tell you a story about a project I worked on earlier in my career. I was responsible for an application that tracks usage of servers in a testing lab. They had a bunch of expensive servers. Engineering departments could request temporary access to these servers to run their tests, and there was chargebacks involved, so each engineering department would share in the cost of maintaining these servers. The application that I wrote was to track who's got the reservations on which servers and for how long. The charges would be per servers. It was a very simple data model. You had a list of machines in this testing lab and the rate per day of how much they would be charged to use them, the users, what department they were from, and then as the users made reservations, it recorded those reservations with a range of dates that they were going to be using that machine. So very simple. Expensive server, Dell R910, $78 a day, reserved by Mr. Coder, he's a developer obviously, for 7 days. And so then he would eventually get charged the balance for that. But the reality was, as the project went on, is that more and more what I called exception cases cropped up. Yes, it was true that the Dell R910 server had a reservation rate of $78 a day, but make the application give them a discount if they also include an accompanying disk shelf, an extra storage unit. But if they reserve it for more than 7 days, they lose that 10% discount. They pay the full rate. Unless it's Department 456, because they are being given a special opportunity to get the discount for the full duration. Unless Department 789 is waiting for the same equipment, in which case they would encourage Department 456 to finish up its work by doubling their rate of reservation. But it's okay if it's during the last 2 weeks of the quarter, because they need to get their work done, and that takes priority. And finally, what I was requested to do is make all of these business rules part of the application and make them data-driven. So store all of the conditions and exceptions and the logic for those rules in the database and have the software adapt to that so that they could apply any of these rules and any unforeseen rules in the future to any combination of servers, departments, or dates. Phew. And this is a little bit of an exaggeration, but it gives you the idea, and you can understand how these types of progressive exception cases to all these policies would grow over time as the project went on and different situations arose. They would have to all build those into the automation for the application. The problem is that in a relational database, you need to be able to represent the very most complex combination of all those rules that could ever occur, even if that's unlikely. And that complicates the database design geometrically. You end up with a great deal more types of attributes to track all those different nuances of entities. The more complex combinations, the more complex your data model, and just it keeps growing and growing. The solution that I advise is use the database for data, not for logic. That is, keep the entities simple. They may have flag attributes, like I call booleans, that say, do they have an exception case to a given rule, and then implement those exception cases in your application code to calculate the final results. It could also be a good use of a domain-specific language. That is, not to build it into data, but to build it into specialized descriptions of the rules, which are then exercised by the application for calculating custom rates for your reservations, for example. And finally, what would have been nice is to say no to some of the complexity. If the number of exception cases is getting out of hand and it becomes more expensive to implement this feature than is warranted, think about what is the opportunity cost. Should we be implementing all these complex rules, or should we be focusing on some other more valuable aspect of the usability or access to that application, or a different application altogether? You could have the same team of developers working on something else that's more valuable to the organization. This is kind of advice for management, because as IT workers, as developers, we may not have the authority to say no to requirements. We're just given the requirements and say, make it work. But we can push back a little bit. As developers, we can say, okay, yes, we can implement that feature for you, but here's what it's going to cost. It's going to take 6 weeks of development and testing, and it's going to double the amount of code that we have to maintain in the future. So there should be some quantitative financial cost-benefit analysis of doing that. If you want to read a little bit more about rules engines and implementing them in a database-driven environment, here's a few things that you can read about. An InfoQ article about rules engines, best practices for implementing them. A daily WTF article about how the enterprise rules engine got out of hand and became something more complex than the application warranted. And there are some frameworks for implementing business logic rules that can actually store the rules in the database, but be careful to not try to use SQL to implement or evaluate those rules. Bring the rules into the application as a domain-specific language and then implement them in the application layer. That's it for today's presentation. And I wanted to remind you that I'm also the author of a book called SQL Anti-Patterns, Avoiding the Pitfalls of Database Programming. That's still for sale. You can get ebooks for that. And finally, remember that Percona has many best practices presentations that are being done at our Percona Live conferences. The next one is in London in November 2014. You can find out more information about how to sign up and the talks that are scheduled at percona.com/live. That's it for my presentation. Do we have any questions in our queue?
Bill, thanks a lot. This is Matt Griffin. We appreciate the presentation on this really important topic for MySQL development mistakes. Yes, so please post your questions there using the tools in the webinar. Also, I'd like to remind everyone that next week we have a webinar on the 23rd of July titled What Every DBA Needs to Know About MySQL Security. So this is a good pair with your webinar today. So this is with Dave Lesby, our security expert on our Percona's managed services team. Dave wrote a very popular blog post about Heartbleed a few months ago on the performance blog. And he's going to share best practices from the operating system to the application layer. So register now and join us next week. And then carrying on from one of the topics that Bill presented about MySQL Fabric, on July 30th, we have a webinar titled Putting MySQL Fabric to Use, where our presenters will discuss MySQL Fabric and then jump straight into live demos and use cases. It's going to be a very interactive webinar, and we will provide vagrant images to install the environment on your local machine so you can follow along.
That sounds great.
Yeah, so it's going to be a nice one. That one's on July 30th. So let's dive into some questions here. I think we have time for one or two questions, and then we'll cover the rest in a follow-up blog post. Mm-hmm. How many tables can be joined in a single query, and is there an optimal way to figure out that optimal approach?
Yeah, MySQL has an architectural limit of 63 tables in a join. So, and that's actually 63 table references. So you could actually be doing self-joins, so it's the same table over and over again, but it's 63 join operations. You'll probably run into some scalability problems long before you get to 63, however. And the guidelines, they depend so heavily on how much data we're talking about in each table, what is the complexity of the join condition, what is the capabilities of your hardware. It's really hard to put a guideline in there. You just have to benchmark it on your environment with your particular query and see how you can go. It may actually be a better plan to see if you find yourself going into a very high number of joins like that, to try to rethink the database design to see if you can accomplish the same thing with a simpler type of query.
Great, great. And then a follow-up question is about how many indexes can be created in a single table, and are there any limitations, and is there an optimal way to figure out the best approach about indexes?
Yeah, there is a maximum number of indexes. I will look it up and add it to the blog post. I believe it's 16 indexes per table, but don't quote me on that. Follow up, read the blog post. I will research it and find that answer for you. As far as figuring out what the best indexes are to use, that can be a kind of meticulous process of analyzing your top queries, the ones that are exercised most frequently or are the highest priority queries that you need to optimize for, and then choose indexes that will serve those queries. Any index design strategy has to be designed with respect to the queries that you run against that table. The good news is, in many cases when I've done that analysis, I find that a single index may be able to help the top 3 queries in a more or less identical way. So you can actually kind of get double duty out of many of your indexes. Of course, this is depends on the type of queries that you run, but it's often able to do that. And Percona support and Percona consulting can really help with doing that query analysis and teach you how to do it yourself too.
Excellent. Great. Well, just want to thank you, Bill, for your time, and thank the audience for joining us today on this webinar. And I'll hand it over to Elisa to see if Elisa has any questions or any additional information to share.
Thanks, Matt, and thanks, Bill, and thank you, audience, for joining. There were quite a few more questions, and Bill will get to them on a follow-up blog post, we promise. With that said, thank you so much for attending today's webinar. Hope you found it joyful and informative, and we hope to see you in the future. Take care, everybody. Bye, Bill. Bye, Matt.
Bye-bye.